Today, many smartwatches support features like wrist-based backlight activation, incident detection, and tracking how many reps you complete during strength training, as well as swim stroke recognition and many other advanced functions. The key reason these features are possible is that multiple sensors inside the watch work together as a system. One of the most important sensors is called the accelerometer. So what exactly is an accelerometer, and why do we need it? Today, we'll walk through how it works and how it's used in real life. Acceleration simply describes how quickly speed changes over a period of time. For example, if motorcycle A accelerates from 20 km per hour to 30 km per hour in 10 seconds, while motorcycle B accelerates from 20 km per hour to 100 km per hour in the same 10 seconds. Motorcycle B has a greater acceleration because it speeds up much faster. If motorcycle C slows from 100 km per hour to 60 km per hour in 10 seconds, and motorcycle D slows from 100 km per hour to a complete stop in the same 10 seconds, then motorcycle D has a greater negative acceleration, or deceleration. Simply put, it slows down faster. We could calculate the acceleration of motorcycle A using pen and paper, but doing that every time would be exhausting. That's why engineers created a device to measure acceleration automatically. That device is the accelerometer. So far, our motorcycle example only involves forward and backward movement. But what if the motorcycle could also move left and right, or up and down? If we place an accelerometer on the motorcycle, and up-down directions, this type of sensor is what we commonly call a 3-axis accelerometer. For a 3-axis accelerometer, there are two types of signals it can detect. The first is static. When a device with a built-in accelerometer is completely still, the accelerometer mainly detects the direction of Earth's gravity. Using this information, the software can determine whether the device is oriented vertically or horizontally. The second type is dynamic. For example, when you're wearing a watch while running, the accelerometer detects the motion of your arm as you move, allowing the watch to measure your running cadence. When we talk about using changes in acceleration to understand events, one classic real-world example is a seismometer used to detect earthquakes. As early as the late 19th century, physicists attached a weighted mass to a spring to build instruments that could record ground displacement, velocity, and acceleration. However, if we want a watch to turn on the backlight with a wrist gesture, or recognize swim strokes, that kind of mechanical structure simply won't work. It's too large to fit inside a watch, and its sensitivity range is also limited. That's why smartwatches use MEMS micro-electromechanical systems. You can think of them as tiny chips with microscopic springs and masses built inside. When you're doing interval training or pushing off the wall during a swim turn, the tiny mass inside the chip shifts slightly, changing its capacitance. The software converts the change into acceleration data and uses it to identify your current activity pattern, barometer, and GPS. The watch can achieve even more accurate posture and motion detection. Now that we understand the basics, let's look at some real-world applications in your watch. Whether you're walking or running, most people move forward with their legs, while their arms swing back and forth naturally to estimate your step count. The amplitude of that motion also helps determine whether you're walking or running, because the watch factors in your height and your historical activity data to estimate stride length. It can multiply that by your steps to calculate distance on an indoor treadmill or while walking indoors. If the backlight were always on, it would drain the battery even when you're not looking at the watch. With an accelerometer, the software can define specific motion conditions, such as the upward rotation angle of your wrist, reaching a certain threshold, followed by a brief pause after the wrist raise. When all conditions are met, the software recognizes the gesture as a check watch motion and turns on the backlight for easy viewing. When you're no longer looking at the watch, and the display moves out of your line of sight, the backlight turns off to save power. When swimming in a pool, the watch relies on the accelerometer to detect your turns, then multiplies them by the pool length to calculate total distance. For example, in a 50-meter pool, if the accelerometer detects 4 links back and forth, that means you've swum a total of 200 meters. However, if your swim technique is irregular, or you collide with another swimmer while passing and come to a sudden stop, the sudden change in acceleration detected by the watch may be interpreted as completing a length, which can cause the recorded distance to increase. During strength training, the accelerometer can also help count repetitions. Take squats as an example. As you lower into the squat, the accelerometer detects downward acceleration. When you pause at the bottom and then stand back up, it detects the pause and the upward acceleration based on this acceleration pattern. The software identifies one completed squat and can further determine which muscle groups were involved using its database. To wrap things up, smartwatches use MEMS-based accelerometers and swim distance tracking, all rely heavily on the accelerometer. Beyond measuring acceleration, changes across 3 axes also provide valuable orientation information. The watch software compares this data with information from other sensors, such as the gyroscope, to deliver more accurate posture and motion detection. That's our introduction to the accelerometer. If you enjoy content that blends science and sports, don't forget to subscribe, like, and turn on notifications. We'll see you in the next video.